Today, we're really getting into something fascinating. It sits right at the intersection of privacy, performance, and honestly, the future of how we interact online. Our mission for this deep dive is to explore how a new technology called WebGPU, how it's really poised to revolutionize client-side cryptography. We're talking about shifting these really powerful computations from the cloud, right onto your personal devices.
Exactly. We'll dig into why this shift is so important, especially for privacy. And we'll look at some surprising technical hurdles that current browser tech, well, just runs into. And then how WebGPU emerges as this powerful solution. We'll cover what it can do now and sort of the road ahead for this technology. It's quite promising.
Right. So if you've ever wondered how your online privacy could get a boost just by using the power that's already, in your pocket or sitting on your desk, well, you're definitely in for some aha moments today. Okay, let's kick off with the why. I mean, this whole vision, client-side crypto, it sounds great. So what's the current picture and why is this shift needed?
Yeah, good place to start. So right now, when you use certain systems, think about things like blockchain rollups, which are basically ways to handle lots of transactions off the main chain to speed things up. Often, your transaction data gets sent off to a central server. It's called a sequencer.
A sequencer, right.
And that sequencer does the heavy lifting. It computes the cryptographic proof and then sends that to the blockchain.
Okay, so it's like a central checkpoint. I can see how that would create a bottleneck.
Exactly. A bottleneck and also a reliance on that single central entity being, well, available and honest.
But the future vision you're talking about, it flips this completely. Users generate the proofs themselves, locally.
Precisely. On their own machines. And then they submit them directly, either to the blockchain or maybe to some managing scheduler.
So what are the big wins with this distributed approach? What do they give us?
Well, the whole paradigm shifts, right? It's moving from crypto in the cloud to crypto at the edge right there on your device. And the benefits are pretty significant. First, privacy. This is huge. Your actual transaction data. It never leaves your device. No third party sees the raw details, not even the roll-up operator.
Wow, okay. That alone is a massive change.
It really is. Then there's scalability. Instead of one server crunching thousands of proofs, the workload gets spread out across all the users. Each person proves their own stuff. So the network actually scales with the number of users. More users, more power.
That makes a lot of sense. Distribute the load. What else?
Cost reduction. Less need for, super expensive central server farms means lower fees for users, ideally. And finally, sovereignty. You get more control. Users can exit a system whenever they want by generating their own exit proof. They don't have to rely on an operator being online or, frankly, trustworthy.
Okay. Privacy, scalability, cost, sovereignty. That's a really compelling package. But it sounds almost too good to be true. Why haven't we been doing this all along? What were the roadblocks, technically speaking?
Ah, yes. The hurdles. It turns out that current browser technologies, especially WebAssembly WASM, the sort of WebAssembly language, and even the CPUs in our devices, they have some pretty serious limitations for this kind of heavy-duty cryptography.
Okay, let's break that down. What are the issues with WASM?
Well, first off, memory constraints. WASM uses 32-bit addressing, which fundamentally limits it to 4 gigabytes of memory. For the big cryptographic circuits and the proving keys needed for zero-knowledge proofs, you can hit that 4 GB ceiling surprisingly easily.
Right, 4 gigs isn't much for these complex tasks. Any other WASM limitations?
Yeah, threading is another challenge. WASM doesn't have, easy native multi-threading built in. You can sort of fake it with web workers and shared memory, but it's clunky for developers. It's not convenient. But maybe the biggest one, critically, is arithmetic inefficiency. WASM only natively supports 64-bit multiplication. It lacks 128-bit multiplier support.
And 128-bit is important for crypto.
Very. It forces the browser to emulate these essential cryptographic operations rather than doing them directly in hardware.
And what's the real-world impact of that emulation? Just a bit slower or?
Oh, much more than a bit. It's a massive performance hit. We're talking for some ZK snark frameworks like ArcWorks in Rust. When you compile that Rust code, which expects 128-bit multipliers, down to WASM, you can see a 25 to 30 times slowdown compared to running it natively in Rust.
25 to 30 times. Wow. Okay, that makes client-side proving sound.
Yeah, nearly impossible, practically speaking. No. It's just too slow to be usable for many applications.
Okay, so WASM in the browser has serious limitations. What about the CPUs themselves, the main processor chips in our phones and laptops? Are they any better?
Well, They're also, unfortunately, not really the ideal platform for this specific kind of work for zero-knowledge proving. Think about the chip itself, the part that actually does the integer math, the arithmetic logic unit, or ALU. It's only about maybe 5% of the CPU's total area.
Only 5%.
Yeah, the rest is cache, control, logic, other stuff. And that ALU is optimized for general 32-bit or 64-bit math, not the very specialized large number arithmetic you need for cryptography, where the numbers, the prime moduli, are often much bigger than 64 bits.
So it's like using a general tool for a very specific job. It works, but it's not efficient.
Exactly. Plus, CPUs have a limited number of cores, right? Maybe 8, 16, that limits how much parallel processing you can do. And research actually shows that this kind of modular arithmetic over large prime fields runs about 10 times slower on typical CPUs compared to specialized hardware.
10 times slower.
So you add all that up, the WASM limits, the CPU architecture mismatch, and you get this huge computational overhead inside the browser. But this is where parallel architectures come in. Things with thousands of cores. They offer a dramatic speed up for these tasks.
Which brings us, I assume, to the GPU, the graphics processing unit. That's the game changer here.
That's exactly it, the GPU. And we've seen just incredible progress in GPU acceleration lately. I mean, just last year, 2023, the top-end NVIDIA server GPUs, like the H100, over 16,000 CDA cores on one chip.
16,000.
Yeah, that's almost a 20x increase since just 2015. And eventually, those kinds of improvements, they trickle down to the GPUs in our phones and laptops. And it's not just hardware, the software is improving too. We're seeing open source GPU libraries pop up like Isakili from Inganama, Spark from Supernational. These are specifically designed to optimize common ZK snark operations like MSMs, multiscalar multiplications, and NTTs, number theoretic transforms.
We're optimizing the core math problem.
Exactly. And things like the Z-Prize initiative, working with Matter Labs, they've also made big strides in speeding up these large-scale calculations on GPUs.
Okay, so GPUs are clearly powerful for this on the server side, but how do we get that power working inside the browser on the client's device? That's been the tricky part, hasn't it?
It absolutely has. Most of the current ZK VMs, the zero-knowledge virtual machines, things like SP1, which uses Plunky 3, they're built for servers. We're talking enormous circuits, over 67 million constraints needing huge amounts of memory, like 128 gigs of RAM. Completely unsuitable for your average device.
Yeah, my laptop definitely doesn't have 128 gigs of RAM.
Right. Now, there are some exceptions trying to shrink things down, like Nexus using Nova folding to get under 4 GB, but often that means the proofs themselves get larger, which isn't ideal either. And this is precisely the gap that WebGPU fills. Client-side ZK acceleration in the browser. It just wasn't really explored because of these limits we've discussed. WebGPU is the technology that bridges that gap. It lets the browser finally tap into the client's GPU for serious number crunching.
So it's not just theory anymore. WebGPU is actually available now.
Oh yeah, it's here. Chrome shipped native support back in version 1.13, April 2023. Before that, it was behind experimental flags. But now, it's usable out of the box. And unlike its predecessor, WebGL, which was really all about drawing graphics, WebGPU makes general-purpose computation on the GPU a first-class citizen. That's the fundamental shift.
A first-class citizen. I like that.
It basically acts as this abstraction layer, letting the browser talk directly to the device's GPU, offloading that heavy work from the CPU and really maximizing the hardware you already have.
That really does feel like a paradigm shift, giving web apps access to that kind of power. So how does it work under the hood? How do developers actually use this? Do they need to become GPU experts?
No, thankfully not. That's the beauty of the abstraction. Developers don't get like super fine-grained hardware control like you would in native CUD programming. Instead, they write high-level shader code. It's in a language called WebGPU Shader Language, or WGSL.
WGSL?
Think of these shaders as the instructions for the GPU, telling it what general computations to run. The browser's compiler then does the really hard work. It takes that WGSL code, optimizes it, and compiles it into whatever intermediate format the underlying system needs. We sort of trust this black box compiler to do a decent job optimizing.
And this black box handles different operating systems and hardware, like Windows, Mac, Linux.
Yep, that's a major strength. Cross-platform compilation. The browser figures it out. It compiles your WGSL shader into, say, HLSL for DirectX on Windows, or MSL for Metal on Apple stuff, or SBRV for Vulkan systems, and then eventually down to the actual machine code for that specific GPU.
It handles all that complexity. That's pretty neat. And what about managing all the parallel tasks? How does threading work in WebGPU?
It's actually very similar conceptually to NVIDIA's CUDA model. The WebGPU API gives you this virtual three-dimensional hierarchy of threads. You can use coordinates in this 3D grid to map onto the vectors and matrices you're working with in your computation.
A 3D grid of threads. Why 3D?
The main goal there is to increase locality. The idea is that work groups of threads that are neighbors in this 3D grid will likely be accessing similar areas of memory. That increases the chances of hitting the cache, which speeds things up significantly.
Optimizing memory access. Makes sense. Okay, WebGPU sounds incredibly powerful, especially compared to the old ways. But what's the reality check? What's its current status? What are the challenges developers are facing right now? And how does it really stack up against, say, the SIMD instructions in WebAssembly you mentioned earlier?
Right, the comparison with WASM-SIMD is really interesting. Based on current observations, WASM-SIMD is probably considered the more, let's say, production-ready platform at this exact moment. It offers more low-level control. Developers can get in there and do finer-grained optimizations than WebGPU's higher-level abstraction currently allows.
Okay, so for fine-tuned control, maybe WASM-SIM still has an edge right now.
Yeah. In some cases, yes. But here's the twist. WebGPU actually outperforms SIMD for the larger circuits, the really complex crypto tasks we're talking about. And perhaps surprisingly, using SIMD in the browser can sometimes even make things slower.
Slower? How can SIMD be slower? Isn't it designed for parallel speed?
You'd think so, but here's the problem. While WASM has SIMD instructions defined, the actual processors in many computers, both x86 and ARM, often don't have native instructions that perfectly match every single WASM SIMD instruction. So what happens? The browser, like Chrome, has to emulate that specific SIMD operation using multiple standard instructions, and that emulation process can actually end up being slower than just running the original non-SIMD code.
Wow, okay, that is counterintuitive. So the abstraction doesn't always map perfectly to the hardware, and the workaround is slower.
Exactly. We saw this on ARM-based MacBooks, for example, implementing a pretty standard crypto operation, Montgomery multiplication, using SIMD. It showed a 2x performance regression. It was twice as slow as the plain Rust implementation compiled to WASM without SIMD.
Okay, so WebGPU definitely has its place, especially for bigger jobs, despite WASM SIMD being maybe more mature in some ways. What are the other practical limitations or challenges developers bump into with WebGPU today?
Yeah, there are definitely things to be aware of. First, hardware differences. Performance can vary a lot depending on the specific GPU and the user's device. That makes delivering a consistent experience tricky.
Right, not everyone has the latest gaming GPU.
Precisely. Second, shader limits. If you make your WGSL shaders too complex, too deep, performance can tank. Or it might even crash the browser or the GPU driver. Chrome version 120, for instance, only supports 10 storage buffers per shader. That's a hard limit you have to design around.
10 storage buffers. Okay, that sounds restrictive.
It can be. Then there's compilation time. Remember that black box compiler? It has to run the first time a shader is used. That initial compilation can take a noticeable moment, which can feel sluggish to the user, although it gets cached after that. Also, browser version variability. WebGPU is still evolving. The standard is maturing, browsers are updating implementations, so performance characteristics can change between versions. You have to keep testing.
Always chasing a moving target, huh?
A bit, yeah. And finally, data pipeline bottlenecks. Often the data you want the GPU to process starts on the CPU. You have to prepare it, maybe convert it to the right byte format, and then send it to the GPU. That transfer and conversion step can itself become a bottleneck, limiting the overall speed up.
Those are definitely important practical hurdles. So given all that, what are the best practices? How should developers approach using WebGPU to get the best results right now?
Good question. Based on current experience, a few principles seem key. First, minimize the number of shaders. Unlike maybe CUDA programming, where you might break things down a lot in WebGPU, fewer well-structured shaders often perform better than many tiny ones due to overheads. Second, don't overload individual shaders. Keep them focused. If a single shader tries to do way too much complex work, that's when you risk performance issues or even clashes. Find the right balance. Third, manage your buffers efficiently. Think carefully about how you allocate and use those storage buffers, especially given the limits. Optimize data transfer patterns. And finally, just be aware of the hardware. Design with the understanding that user GPUs will vary. Aim for something that works reasonably well across a range, rather than something that only flies on the absolute highest end hardware.
That's solid advice. Minimize shaders, keep them focused, manage buffers, and be realistic about hardware.
Yeah, that sums it up pretty well for now. So, wrapping things up a bit, WebGPU really does present this powerful new avenue for building privacy-preserving apps. especially thinking about platforms like Ethereum and ZK rollups. The potential for client-side zero-knowledge acceleration is immense.
It definitely sounds like it, but it also sounds like, it's still evolving. The API isn't set in stone yet.
That's right. The W3C standard is still actively being developed. The latest versions are quite recent. And there are real technical challenges. For instance, developers often need to implement the low-level cryptographic math libraries pretty much from scratch for the WGSL environment.
Right, you can't just plug in existing libraries easily.
Not always, no. So, while it's incredibly promising, it might not be quite mature enough today for, say, building absolutely bulletproof, production-ready proof generation protocols from the ground up. But it's getting there fast. And one final point of nuance, while having the user generate proofs locally is a massive step for decentralization and privacy. It's worth remembering that in many current designs, the system still often relies on some kind of off-chain operator or scheduler.
Ah, okay, so there's still a coordinator involved.
Yeah, someone to manage and merge all those individual proofs, make sure everything stays consistent with the main blockchain state. So WebGPU helps offload a huge chunk of work and massively boosts privacy, but it doesn't necessarily remove all centralized components in one go. It's more like a very significant step on that path.
That's a really important clarification. It's a major shift, but maybe not the final step towards complete decentralization in all cases. Well, this has been a fascinating deep dive. We've seen the limitations of older tech and the truly incredible potential WebGPU unlocks for moving these complex, privacy-critical computations right onto your own device. And it leaves us with a question, really, for you, the listener. As this kind of client-side proof generation becomes more common, more feasible, how might that fundamentally change your expectations around privacy, around data ownership, around the very nature of how you interact digitally in the future? Definitely something to mull over until our next deep dive.